All right. I'm glad to see that many of you have brought your computers for today's class. That's going to be useful when we get to the in-class exercise. But you do not need to bring one on Friday. We're just only going to be doing some paper stuff on Friday. So I'll try and make the announcements in advance. And so the homework assignment number 5 is due on Friday. And I have office hours today, tomorrow, and Friday, so please let me know if you've got any questions. I'm anxious to help you out. If you didn't already pick up your homework assignments, you can get that at the end of the class, but just to mention, our grader has a big job this semester, grading 47 students' homework, and some of these are pretty lengthy homework assignments, as you know well. And so if the grader makes a mistake while grading your assignment, please let me know if you feel like you've been shortchanged on the points. Someone else is grading the homework, but I want you to feel like your work has been graded fairly and accurately. So please stop by during my office hours if there's anything that I need to address. Any questions? Any questions related to today's announcements before we get into the new material? I guess the main thing is the homework that's coming up. And that's mostly a computer-based homework, so it should be relatively quick if you've been following along. All right, so here's what we're doing today. We're going to continue talking about spreadsheet functions and learning how to apply some of these cash flow diagrams into Excel problem solving. So let's take a look at kind of where we left off with the in-class exercise last time, where I had asked you to create a solution strategy. You didn't actually try and solve for the present value, but you were trying to figure out what you would have to do if you were going to solve for the present value. So in this case, you can see here's a cash flow diagram that has 2 pieces. It's got an annual series in years 3 through 9, and then there is a single one-time future value of 2,000 in year 8. Let's see, 1, 2, 3, 4, 5, 6, 7. Yeah, year 8. Okay, so in a case like this, you would need to recognize the components that there are. There's the annual series, also known as the uniform series, and then the single amount. And so we have to combine them in the end to find the present value of that. And so the steps are, first of all, you may want to renumber time, just with kind of a quasi-zero year. And you'll notice here that they've renumbered time and they've put like a secondary time axis so that year 0 is here at 2. Actual year 2, we're calling year 0 because that's the first year before the annual series actually began. And so we can't take this annual series all the way from where it is right now to year 0 in a single step. We have to do it in 2 steps. We have to first of all take the annual series to year 2, and then from year 2 to year 0, just because of the way that P/A works. P/A, remember those pre-existing formulas that are in the back of your book and the table lookup factors that correspond to them. And so our solution strategy is first of all to find the present value of the annual series, so 5,000. And you'll notice that within the brackets, we've summarized the problem that we're going to be doing. We've summarized that this is find the present of an annual series. Now, when we say present, the P that's listed here isn't the actual 0-year present, but it's the present of that secondary time axis where we have 0 underneath year 2. So it's not really the final present value that we need to know, but it's present from within the viewpoint of the annual series. Okay, so P/A, find the present of an annual 10% interest where n equals 8. So there are 8 payments. It's going to take it from the annual series to a single amount in year 2, which is quasi-year 0. So we can multiply the 5,000 by the factor and get 26,675. Now, the single value that now has been moved to year 2 can be jumped to year 0 in one step, where we want to find the amount in year 0. That is our present value. But now what we were just barely in the previous step calling a present, now we're calling that a future. Because now instead of looking at our quasi-time axis of this secondary 0, 1, 2 that's underneath the main time axis, we're now looking at the amount in year 2 as a future amount, which it in reality is. It's a future amount, and so that's why now we have P/F, is we're taking it from year 2, which is the future, to the present. And so that's why we have n equals 2 for that second step. Now I know that this is unfamiliar and maybe complicated at first, so are there any questions, or anybody need me to take another stab at trying to clarify that? The 2,000 is easier. We can move the amount of 2,000 just in a single step. And so that goes from year 8 to year 0. And so here n equals 8. We don't have to refer to the secondary time axis because you can move a single amount in just one step, unlike the annual series. Now you can move an annual series in one step, but that's only if it starts in year 1. This annual series didn't start in year 1. It started in year 3, and that's why we had to, first of all, take it to a single amount in year 2. And then you add the two amounts together. The effect of the single payment and the effect of the annual series are combined all together in year 0. All right, gradients we can do the same thing with. If they are shifted away from where they belong as far as the 0 time axis is concerned, we can move them to a quasi-year 0, and then from that quasi-year 0 to actual year 0. Now just a note, remember that the first time you see the effect of a gradient is in year 2. So 2 years after point 0, and so the present, what we're going to call time 0 from the perspective of a gradient, is 2 years before the first time you see the gradient amount. Okay, so here is a cash flow diagram that has both a gradient and an annual series combined. So you can see that the annual series, every year there's 60, whatever it is, dollars I guess, $60 in year 1 through 10, but then there also is this increasing amount of 5 in each subsequent year, starting with year 4. Okay, so the question is, where should we set as our secondary year 0? What should be, you know how I, in the previous example, had a different set of numbers under the main time axis? Where should 0 go this time? It's kind of tricky because remember, the first time you see the extra 5, that is year 2 from perspective of the gradient. So we see the extra 5 here in year 4. So that means this is year 2, which would make year 3 would be where we see 0g. That's why it's still just 60. And so our year 0 from the perspective of the gradient is here in year 2. So that means we're going to take the gradient to year 2. And what about the annual series? Do we have to break that into steps, or can it all go to year 0 in a single step? Anybody feel like they know? The annual series, the amount of 60 every year. Does it have to be in steps, or can it go all at once? All at once, that's right, because it is right next to year 0. It is present in year 1, and so when we move it to the present, it's going to be just 1 year before the first time we see it. Okay? The gradient, on the other hand, the first time we see it, present is 2 years prior to that, instead of just 1 year prior. Okay, so we have to find the present value in year 2 for the gradient amount, and so we do that by, first of all, finding, well, there's always more than one way to solve a problem, and here what they're saying is, instead of taking the present value all to year 0, they're saying take the 60, 8 units of that to year 2, and then also combine it with the gradient amount of 5. So it's kind of splitting the timeline into everything before and after our year 2. And that's what one of the things that will complicate these problems is that there's not only just one way to solve them. So here we are moving everything from years 3 and onward to year 2, and then that means there's going to be 2 payments of 60 left over, and so those are these 2 payments of 60 that are taken to the present, and so altogether it's 396 and 70 cents. All right, so here is your first problem. This is the same cash flow diagram that you were looking at last time, but this time I'd actually like you to solve it. And so there is a factor table on the back of the paper. It is the 8% factor table, which you can use to find the present value of that cash flow diagram. Now this one's not on the computer. This one is by hand. Once you do it on hand, you can double check your work on the computer if you'd like. That's a convenient way to make sure you're doing it right. But for the first try, it's really important that you learn the skill of how to solve these by hand. There's more than one way to solve these, and so you don't have to do it my way to get the right answer. You could have started, for example, with the outflows instead of the inflows. In my case, I started with the inflows, but you don't have to do it that way. It's awfully hard to see from the back here. Okay, as I was wandering around, it seemed like there were a few people who were doing it the hard way. We're actually solving the equations. Let me emphasize what these tables are for. You don't have to actually solve the equation for example, P/G. That's a complicated equation if you're actually trying to find the factor. What you can do in the solution, just for instance, I had a P/G 8% n equals 4. So I would go to here in the table, find P/G, n equals 4, and it says here 4.6501. If I multiply this factor of 4.6501 by the gradient value, which in this case is 1,000, then it will tell me what is the present value of that 1,000, and that is where this amount came from. The amount that I'm calling D. So sometimes you'll have to use those equations, other times it'll be about the factors. All right, let's move on to the second question. There's a cash flow diagram that I would like you to use in Excel. So start up Excel. And by the way, you can come back to this problem 1 anytime you like. The solution is on the video if you need to come back to it. But just so you also get some chance to use Excel, even if you're not finished with part 1, let's move on to part 2. Okay, so the column headers for this one, since this is something we're going to be finding the future value, we first need to give it an interest rate cell, and then years until year 16, amount, and FV. Okay, the interest rate in the second problem is 6.25%, so it should be 0.0625. And then we have a cash flow diagram that goes years 0 through 16. So 0, 1, drag it down until you get 16 of them. And then an easy way to do this one is just equal 16 minus whatever year you're on. And remember, the whole purpose for this reverse order time is it tells us what our n should be when we're finding the future value. Just for example, something in year 1, it needs to go 15 years into the future to take that amount to year 16. It doesn't need to go 1 year in the future. And so if I used n equals 1, then I'd be telling Excel the wrong number of years to carry it into the future. That's why I have to have that secondary time axis. Okay, so we can just put in the amounts now. Yes, indeed. I need to put an extra 0 there. On the part B, it says, after solving for part A, determine what interest rate would make the future value 100,000. You can either do that over and over and over lots of times, or you can use goal seek. So just to refresh your memory where to find the goal seek, essentially what we're going to be doing is we're going to be changing I until this future value is 100,000. So right now, when I is 6.25%, then that gives us a future value of 61,157. We're asking, what would the interest rate have to be in order to get 100,000? Okay, so we go to Data, What If Analysis, Goal Seek. And then it's asking 3 things. First of all, it wants to know what's our target. So the target cell, the one that we're trying to get to the number we have in mind, is here. This amount that is the sum of all the future values. So that's the target, and the amount we want it to reach is 100,000. And then the final thing it needs to know is where in the spreadsheet can it go and play around with some number over and over, iterating until it achieves that goal. So it's asking, what is it okay to change? And we're going to tell it the interest rate. Change the interest rate. So as soon as we click OK, it's going to start putting in lots and lots of values until it converges, until the numerical solution that it finds is equal to our goal. So we click OK, and very quickly it finds that it would be 17.2%. And so the second part, part B, so this first one was part A. Now for part B, it is for a desired FV of 100,000, I equals 17.25% is required. All right, let me just show you one more thing. if your column isn't wide enough, sometimes it'll give you these weird pound signs. So if you ever see them as you're working with Excel, that sometimes just means make it wider. And if you don't want to know exactly how wide it should be, you can just double click at the top and it'll make it as wide as it needs to be to fit all the information that's there. Okay, so the last part, for part C, the question was, why must the interest rate increase in order for the future value to increase? That's because we're compounding all of these amounts into the future. And so if you want a bigger amount in the future, you need a higher interest rate. You can think of it as a savings account. If you want to have a big account balance in the future, if you want to have $100,000 instead of $61,000, then you'd need to have a higher interest rate. Just as a reminder, you do not need to bring your computer next time, but you should bring the completed homework assignment. So let me know if you've got any questions with that. If you didn't already get your graded homework, those are here at the front, and I'll see you next time.